Hello, it's me again, Sam Moore, back one more time with our series on your electric guitar, the internals of your electric guitar. How does it work without using math? Uh, been away for a couple weeks. It's been Christmas. I've had a good time. I've enjoyed myself. I hope you did too. So, belated Merry Christmas. Hope you scored a bunch of good stuff. I did. I got this cool PC oscilloscope. That's PC. It plugs into your personal computer, into a regular IBM compatible PC, and you can actually see waveforms. If you look at the beginning shot in this video, the first 6 seconds, or approximately 6 seconds, you'll see a screenshot that I took where I actually hooked it up. I plugged it into my PC. I got my electric guitar out, and twang, I captured a waveform. So you can see the waveform, the output of the guitar. The tone control is turned all the way off, so it's just a straightforward output of the guitar. And you can see the sine waves, just like we talked about when we talked about Fourier construction and deconstruction of waves. So that's kind of cool. We'll be seeing more of that later, as we go along. But it's good stuff. It's made by a company called Handtech, which is, of course, Chinese. Everything seems to be Chinese. What are we going to do this week? I've been promising, so it's finally here. We're going to talk about capacitors. That is one of the basic components of your guitar, and it's an important one. It figures into the tone circuit, and how the tone circuit works, and fun stuff like that. Watch this. You're going to love this. It's going to be really cool. Hold on. This is a piece of aluminum foil, just like you get out of your kitchen. Here's another piece of aluminum foil. This is a piece of wax paper. Again, right out of your kitchen. Just regular old, ordinary, everyday wax paper. That's how it goes. Let's take our piece of aluminum foil and lay it down just like that. Now let's take our piece of wax paper and lay it on top of it, just like that. Okay. Now let's take our second piece of aluminum foil, just like this, and lay it on top of it. I just built a capacitor, folks. You saw it here first. Ta-da! Ba-dum-ba-dum-bum-bum. Yes, you saw a hillbilly build a capacitor in front of your very eyes. In other words, a capacitor is nothing more than a piece of conductive material, and then an insulator or a piece of non-conductive material, and then another piece of conductive material. Doesn't matter what shape they are, doesn't matter how big they are. The bigger the plates, the conductive material of the capacitor is called the plates. The bigger the capacitor, the bigger the capacitance. The insulating material, the wax paper and my homemade capacitor is the insulating material. The thinner the insulating material, the closer together the plates are, the higher the capacitance. Thicker insulating material, lower capacitance. Doesn't matter what shape they are. These are just long and thin because I wanted them long and thin. Why did I want them long and thin? Because I'm going to roll them up, just like a cigar. Being careful not to let the two conductive plates touch each other. Just roll them up. Look at that. There they are, rolled up. Now I'm going to put them in, you knew it was coming, a tube. There we go. Now I have a tubular capacitor, but it's still two conductive plates separated by an insulating material. Okay, pretty cool, huh? The schematic symbol for a capacitor. If you see a circuit diagram and the circuit has capacitors in it, of course there's a schematic symbol. That's the schematic symbol for a capacitor. I don't know. Yeah, you can see it there. Now then, you see you got a straight line, a curved line, and these are the wires that thing ties into the circuits with. But that's all it is. Sometimes people get lazy and they draw this line straight. I try to not do that because it becomes a little confusing. You can't tell a capacitor from a battery, if you draw it straight. But sometimes they draw that straight. But I'll always try to draw it curved. like it's supposed to be. Now, well, what does it do? That's a good question. That's a good question, because this is a hole in the circuit. You got conductor over here, and you got conductor over here, and you got insulator between them. It's a hole in the circuit. It looks like the electricity couldn't get through there, you know. It's a hole in the circuit. Well, what does it do? Okay, a capacitor stores charge. That's right. It stores electric charge. It's kind of like a bucket for electricity. If I come in here and I put a battery on here and tie it to this capacitor with a piece of wire, here's our battery over here. Let me diddle that around to where you can see it. Here's our battery over here, and it's tied to the capacitor with a piece of wire, and it's tied to the capacitor with a piece of wire right here. Then it stores charge. In other words, the electrons come running out of here, and they come running around there, and they get on here. Okay, and the positive charges come running out of here, and they come running around here, and they get on here. And they just run around there. Now, they can see each other across that insulating material. I mean, hey, it's wax paper. You can see through it. No, electrically, they see each other electrically. They see their electric field. We can come in here and we can take the battery out, and those charges will stay right there. They'll sit right there on that capacitor. They're stored. So a capacitor is just a charge storage device. Pure and simple. It's that easy. There's nothing magic about it. Storage charge. Now, the units of capacitance are farads. And there is, of course, a mathematical formula, just like everything else. But I told you, we're going to avoid math, and I'm still going to continue to do so. It's the units of capacitance are farads. C is equal to Q over V, or the capacitance in farads is equal to the charge stored for each volt that you put on there. You put 1 volt on there and you store 1 coulomb of charge, then you've got a 1 farad capacitor. Now, those units for capacitance are too big. When they named them, they got a little wild, you know, when they pick units that are just too big to be practical. So you usually hear capacitors size, and people talk about the capacitance size. They talk about microfarads, which is 10 to the minus 12 farads. They talk about picofarads, or sometimes if you get somebody who's got a lot of this platinum blonde hair, they'll talk about microfarads, which is 10 to the minus, I got that backwards when I wrote it down. Microfarads is 10 to the minus 6. 10 to the minus 6 farads. And they talk about picofarads, which is microfarads, which is 10 to the minus 12 farads. So you can see those are much, much, much smaller numbers than farads. Every now and then you'll hear somebody talk about nanofarads, which is 10 to the minus 9 farads. That's not really used very much, but every now and then you'll see somebody use nanofarads. It's kind of rare, and it's kind of a weird unit. But usually you see microfarads, 10 to the minus 6, or 1/millionth of a farad, or microfarads, 10 to the minus 12th farads. Let me see. Now, stores charge. Kind of like a bucket for charge. What does it do? Well, it does the same thing as a water bucket. Yeah, just stores charge. I've got a cool educational aid, a teaching aid here that I'm going to show you. Now, I've spent a lot of money developing this teaching aid, but if you want to use it, just contact me and we'll talk about licensing it to where you can use it too, should you ever want to do this. But now I'm telling you, I spent hundreds of thousands of dollars developing this. So don't be just going out and using it willy-nilly, you know, without talking to me first. Okay, here's my cool high-dollar teaching aid. I've got 2 buckets, 1 bucket, 2 buckets, and they're tied together right here with a little pipe or a little hose. Now let's empty these buckets out, or mostly empty these buckets out. Okay, if I come along in here and I pour water into this bucket, that's dirty water, glub, 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 glub. What's going to happen? That's right. Water's going to run through this hose right here, and the water in this bucket's going to go up too. Glub, 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 glub. Pretty cool, huh? Okay. Now, if I dip water out of this bucket, dip, 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 what's going to happen? Water's going to run through here, it's going to run through here, and into this bucket. Okay. And the water level in this bucket is going to go down too. Magic, huh? Put water in here, bloop, bloop, bloop. Water in here is going to come up, bloop, 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 bloop. If I don't change the water level in this bucket, if I let it just sit there at that level, what's going to happen to the water level in this bucket? Nothing. It's going to sit there just like it was. If I change the water level in this bucket, what's going to happen over here? The water level in this bucket is going to change. Anytime I change this, this will change. If I do not change this, nothing is going to happen. So, water only flows through this pipe when the water level here changes. And whenever the water level there changes, the water level there is going to change, and water, a current of water, is going to flow through the pipe. No change, no current. Now, let's go back to the electrical world. Here we are back in electrical world. Here's our capacitor again, right here. Here's a voltage source, a battery, right here. Now, this capacitor and this battery behave exactly the same as our two buckets. Turn on this voltage, the capacitor is going to charge up. It'll charge up to be exactly the same voltage as the battery. The buckets will fill to exactly the same level. If I change this voltage is going to change. Whenever that voltage changes, that means charge is moving out of the battery onto the capacitor. Okay, what is a moving charge? It's a current. It's an electric current. Change the voltage, current will flow to charge up the capacitor or discharge the capacitor. And while that voltage is rising and while that voltage is falling, current is flowing. Okay? But current only flows when the voltage changes. The water only flows when the level in one of the buckets change. Hey, you change the water level, then you've got a flow of current in the hose. Water current. Change the level, water current flows. Change the voltage, electric current flows. Electric current only flows when the voltage changes. Next time, we're going to simulate some circuits. You remember our voltage, our circuit simulator that have voltage sources in them and capacitors in them, and actually resistors in them. Because what does a resistor do? Remember, it holds back that current flow. So just like changing the size of this hose will change how fast the water flows from this bucket to this bucket, and change how long it takes this bucket to charge up and discharge and empty, then changing the resistor will change how long it takes the capacitor to charge up and discharge. So next time we're going to simulate some circuits. We'll talk about the RC time constant, as it's called, now let's see what we talked about this time. We talked about a capacitor is a charge bucket. All it does is hold a charge and store charge. We talked about how if there is no change in the voltage, in the applied voltage, there's no current. The current only flows when the voltage changes. And we talked about a little bit about our buckets, or our cool educational aid, or our cool teaching aid. I still think that's a pretty cool teaching aid. And I'll be reasonable on the licensing fees, if you want to use it. Until then, keep on picking.